a Portland Community College mathematics telecourse. A course in arithmetic review, produced at Portland Community College. Can you see that just by the title alone that this lesson is going to be simply a subset of the previous lesson? After all, fractions are implied divisions, and we've already had that. So the last lesson, which was a bit long, will make this lesson to be that much shorter. So we simply read this as 3 divided by 8 and write it accordingly. And then we call the decimal points on the end of whole numbers. Since I'm dividing by a whole number, this decimal point goes straight up. I can append as many zeros as I wish, and then simply divide. And to save you time, I'll do it separately. And we find after 3 divisions, it comes out evenly. Hence, we have a terminating decimal representative of the fraction 3/8. Again, all fractions are in disguise a division. Another one, 4 divided by 11ths, more commonly said 4 11ths. So setting it up in its division form, we get this, and doing the division, we begin to get an unending quotient. However, we can see the repetition. The repetition is at 3/6, so we could write this as 0.36 with a bar over it. Or whoever is using this might make a statement like this: round to the nearest thousandth. So in a case like that, we go out to the nearest thousandth, look only at the digit next to it, and that is 5 or more, so we add 1 to the thousandth position, which is 4. And so here we have a rounded approximation of 4 11ths, accurate to the nearest thousandths. Some books will show that with a symbol like this. Others will use a symbol like that. Both of these are symbols which mean approximately equal to. Again, a fraction is really a division in disguise. Another one, 2 and 5/16. That's one way of saying it. Another way of saying it would be 2 and 5 divided by 16. Decimal points on the end, shoot it straight up, add as many zeros as you think will be necessary, and begin to divide. And in this case, we get a terminating 0. So we can say 2 and 5/16 is 2 and, or 2.3125, in this case, exactly. Here's an interesting fact regarding repeating or terminating decimals. The fact is this: a fraction whose denominator has only 2's and or 5's as prime factors, that is divisors, will result always in a terminating decimals. All others will be unending repeating decimals. Interesting fact. Let's look at some examples. If you divided 7 by 32, it would come out to be 0.21875. It goes out quite a ways, but at this point it quits. It terminates. And notice that its denominator prime factors into 2 to the 5th, which means 2 is the only prime number that divides 32. Now it's the same thing with 11/500ths. If you were to divide that out, it would come out to be 0.022, and it quits. And if you were to prime factor it, it's 2 to the second power times 5 to the third power. Hence, the only prime numbers that will divide 500 is 2 and 5. And that's what our special note said. If 2 and 5 are the only divisors, prime number-wise, of the denominator, it will always terminate. Sometimes it terminates rather soon. Sometimes it'll go quite a ways before it terminates, but it will always terminate. Here's a rather cute shortcut for some fractions. Let's say we wish to change this one into a decimal. But first note, if I were to multiply top and bottom by 5, the top, of course, becomes 35, and the bottom becomes 100, a power of 10. Then in that case, recall back a couple of lessons, I can simply make the top smaller by 2 decimal places, or 0.35. And sure enough, if you divide 7 by 20, it comes out to be 0.35. So sometimes you can sort of watch the denominators and ask, is there any number I can multiply it by that will make it become a power of 10? Because if I can, all I need to do is move the decimal point instead of dividing. And that's quite easy. And that kind of fraction occurs very frequently in business fractions. Can you see that here? If I were to multiply 500 by 2, it becomes 1,000. And 2 times the top is easy to do mentally. 10 carry the 1, 3, 6. But if I'm dividing by 1,000, that's the same thing as making the top smaller by 1, 2, 3 places, which is 0.63, because in fact I don't need that end 0 now. So in your work in other classes, particularly bookkeeping and some of those, watch for that kind of a denominator. And frequently you'll be in a position to do this kind of a problem with a calculator. Here they want it rounded to the nearest 10,000th. So that's 6 and, here's 6 and 37 divided by 89. So on your calculator, 37 divided by 89 equals. And you get, of course, a very long decimal answer. But according to our instructions, we don't need all of that. We need it rounded to the nearest 10,000ths. So let's see, 10th, 100th, thousandths, 10,000ths. Look at only the one to its right. It's 4 or less, so I can drop it. So there I've converted that mixed number to an approximate decimal, accurate to the nearest 10,000th. Let's play with a couple of problems where this kind of skill is really very necessary. Consider this one. A shop micrometer reads to the nearest thousandth of an inch. A bolt is supposed to be 27/32 of an inch in diameter. What would be the reading on the micrometer? Now, I don't have a micrometer here, but perhaps you could, if you haven't seen one, you can get the idea. Here's a bolt, and a micrometer is basically a tool like the C-clamp that you would tighten up onto the boat. And as you were doing that, you would have a scale here where it reads these turnarounds in terms of the distance that's going down. And because of that, you can get this so it reads very, very accurately to the nearest thousandth of an inch rather routinely. And in some specialized cases, to the nearest 10,000th of a case. The point is, many standardized bolts come marked with their diameter in 32nds or 64ths. but most standard micrometers will be calibrated to read in the decimal system. So you're trying to check the bolt to see if it really is this diameter, then what would you expect to see on the micrometer? So our problem is basically this, stated arithmetically. And that is to simply convert 27/32 to a decimal, accurate to the nearest thousandth. And now, to do that, all we have to do is remember that this symbol means divided by. But let's also note this. 32 is divisible only by the prime number 2. That means if I were to divide 27 by 32, it will terminate at some point. Well, this reads 27 divided by 32, decimal points on the end, go straight up. I want it to the nearest thousandth, so here's tenth, hundredth, thousandth. However, in round-off situation, you always go one digit further to see if I round up or back. Now, doing this division, you would get these 4 digits. Actually, there's one more there, but since we want it only to the nearest thousandth, all we need is one more digit, and since that's 5 or more, we would add 1 to this. So that means if you were trying to read this, and if this were actually the diameter of that bolt, then on the micrometer, the best we could see is 0.844. It'd be closer to 4 than 3, because this 7 is closer to 4 than it is down to 3. So you see by this, whenever you, in a textbook, see a problem that looks like this, that seems to be rather sterile and out of the real world, it's important to know that they really do come from real-world situations. Another one. There are decimal rulers which read to the nearest hundredth of an inch. Then on such a ruler, what would 7/16 read as? Because most standard school rulers will read to the nearest 16th or 32nd. But you might look around a shop the next time you're near one, see if you can find one of these decimal rulers. They're fairly common. Well, we simply, again, remember this means divided by. So that reads 7 divided by 16. And what the problem is stating is that the ruler can't read anything beyond 100, so whatever is beyond here really is irrelevant to the ruler. But we do need one more digit here to find out whether the ruler will read to the next highest or the one down below. So performing this division either by hand or by calculator, you would get 0.437 and so on. But again, we only need one more digit to tell this is more than 5, therefore we round this up. So we can now claim that 7/16 is approximately equal to the decimal number 44. That is closer to 0.44 than it is to 0.43. So on our decimal ruler, this is actually what we would see. We see it, the edge of our measuring item just almost against the next 4 in the hundredths place, just a squidge under it. Here's an interesting problem. A science book, most of them, gives the value of this symbol, which we call pi, as 3.1416. You use this number a whole lot when working with spheres and circles. Whereas another book says to use 22/7. Can one really do this? That is, what we're really asking is this. Is 22/7 really equal to 3.1416? Assuming that this is correct, that is accurate to the nearest 10,000ths, Well, let's check this. You might recall many elementary schools used this as a value of pi before you got into decimals at the later grades. Well, let's divide 22 by 7 and see if it comes out to be this. So 22 divided by 7, decimal point is here. Let's go straight up. Let's actually divide it. And if I do so, I get this quotient. And let's compare them, and you actually will get a feel now for what round off really means. We see they agree at the whole number, they agree at the 10th, they agree at the 100th, but at the thousandths they disagree. However, if I were to round this decimal value of pi to the nearest thousandths, this would round to 2. Of course, this one would round to 3, doesn't it? So what we can really say is that 22 sevenths is approximately equal to pi. And we can say more than that. We can tell you exactly how approximate it is. So the correct statement is that 22 sevenths is not equal to pi. However, it is correct to say that 22 sevenths is approximately equal to pi to the nearest hundredth. So if this amount of accuracy is good enough, you could use this fraction as approximator. If you need more accuracy than that, then this would be not good enough. By the way, while we're here, let me show you a cute device to remember pi to as many places as you need within normal usage. If you remember the phrase, may I have a large container of coffee, phrase many people use, then count the letters, 3.1415926 out to that many places. In fact, that's what pi is equal to. Whereas 22 sevenths, if we were to work that with more accuracy, we would find that it is approximately equal to that decimal. And again, you can see that they agree out to the nearest hundredth. Beyond that, pi and 22 sevenths are entirely different numbers. So if you can remember this phrase, an easy one to remember, that will give you pi to quite a few places. Let's see if we can verbalize this. 10th, 100th, thousandths, 10 thousandths, 100 thousandths, millionths, 10 millionths. So this phrase gives you pi to the nearest 10 millionths. More accuracy than you would use in most sciences. By the way, a question frequently asked of me in class at this point is, where does that pi, that number, come from? How does that fit into mathematics? Well, if you don't know, it's very simple and very interesting. Well, if you were to take any circle and start on the rim and measure its distance around, which we call a circumference, let's call that capital C, then measure the distance across the circle that goes through the center, which we call the diameter, and call that D, and divide these two. Depending on how accurate the circle is drawn, it would come out close to that value of pi, 3.1416, etc. Actually, it's 159, etc. And of course, that rounds to 6 at the nearest 10 thousandths. The more accurate that circle was, the closer it would be to pi. And the size of the circle had nothing to do with it. If you were to take a smaller circle and measure its circumference, let's call that small c, and then its diameter, which of course would also be smaller, and divide these two, the ratio would again be that number pi. So the definition of pi is nothing more than the ratio, or the number you get when you divide the length of a circumference by the diameter. And using fairly advanced math, we can prove that this number, which goes on forever, is approximately equal to that number. And interestingly enough, that number, 3.141596, etc., is not a repeating decimal and is not a terminating decimal. It's a very interesting number, and advanced mathematics spends a lot of time studying and using it. But nevertheless, here we have a decimal number that goes on forever, and very frequently we need that number, but we of course can't go on forever, so we must specify where we're going to quit. And that's nothing more than what this in the last lesson is about. That is, rounding decimal numbers. Therefore, it is necessary that by the completion of this lesson that you realize to ask a simple question like changing a fraction, two of them here, into a decimal is not enough. Because if you were to do that by performing the division, in this case 7 divided by 19, or in this case 3 divided by 40, we now need to realize that as I do either one of these, that I realize that I will get either a decimal that goes on forever, with a repeating cycle, of course, somewhere in it, or a decimal that might go on a very long way. For instance, in this particular case, since 40, the denominator, has only 2's and 5's as prime divisors, this will be a terminating decimal somewhere. It might go out a long way. And this one will never terminate. It will keep on giving me digits forever and ever. So whenever I'm converting a fraction to a decimal, and I intend to use that answer, I have to quit somewhere. So at this point you realize that it's not enough to say simply to change to a decimal. You must specify where I am to quit. That is, where do I want to round? How much accuracy is needed? And that has to be specified to you external of the problem. There are no math rules telling you where to round off. It depends on what you want to use that decimal equivalent for. So in this particular case, let's assume that somehow someone has determined it needs to be accurate to the nearest 10 thousandths. So therefore, as we perform the division, we'll go out to the nearest 10, 100 thousandths, 10 thousandths, and one extra digit. We don't need this now to find out whether I round up or down. In this case, if I were to follow through with that, I would get this, and the next digit is less than 4 or less, so I round down. So 7/9 to the nearest 10 thousandths is the decimal point 3684. And it's very important to realize that this is not exactly equal to that, but it's closer to this than to 3683 or 3685, that this is the closest approximation at that place. Then doing the same thing to this fraction that we wish to have as a decimal accurate to the nearest 10 thousandths, we would get a situation where it actually terminated before I got to the nearest 10 thousandths. However, as I wrote this, more likely I would not terminate it here, but actually to insert a 0. Because when I say that it terminates, what I'm really meaning is I finally get zeros as my repeating digit from that point on. So in a sense, a terminating decimal is one in which 0 is the repeating portion. And if you were to give an answer to somebody, that means you're going to give them this without this, so they don't know that it came from a fraction that just happened to terminate at the nearest thousands. If you needed 10 thousandths, you need to tell the person you're going to give this to that, hey, that 10 thousandths digit is a legitimate and accurate zero. So sometimes, even though a zero does not contribute to the value of a number, it is necessary to keep it in order to convey how much accuracy you have to the person to whom you're going to give this number. And do remember that if whole numbers, mixed numbers, are involved, that the whole number part doesn't enter into the computation. It simply is the whole number of the decimal. Then to find the decimal portion, we work only with the proper fraction portion. So 3 divided by 11. And in this case, let's see if a pattern comes out. We haven't followed through too many to find that pattern. But if we wanted the nearest hundredth, we would normally go only to the hundredth and then one extra to see where the round off is. So let's see, 11 into 30 is twice, 22, 8. 11 into 80 is 7, 77, 3. 11 into 30 is twice. And at this point, you can see I got 30 here, then 80. I've got 30 here and 80. So in fact, it's the 27 that's going to repeat. But in fact, we want it only to the nearest hundredth. Digit next to it is 4 or less, so I drop them. So this is approximately equal to 2.27. If, however, I were to say this, 2.27 with a bar over it, where now we understand that the bar means to go on with this pattern forever, then we can say more than being approximately equal. We can say it's exactly equal. So that's a convenient notation, isn't it? Okay, so this lesson is a very simple one of the simpler you've had. It'll give you lots of practice of division and, of course, rounding off. But it's one that's used a whole lot in shops and in industry and, to be sure, in science. In the next lesson, we'll show you yet another way of showing a fraction as a decimal in an exact way. A method you perhaps haven't seen before, but is used frequently in stock markets. So, until then, this is your host, Bob Fennell. Good luck.